Okay. I'm going to add a little bit to our little lecture series on Eilenberg MacLane spaces. And let me share my board, of course. There we go. So yeah, the bar construction as I gave it, it's a geometric view. Our EG is its chains give a resolution of the ground ring over the group ring, if you want. And the geometry was in sort of visualizing those chains and especially in visualizing the iterated bar constructions chains. Well, there's actually a geometric reason to be looking at that construction outside of the construction of classifying spaces. It's pretty surprising, actually. There's something in the background called causal modality that I might talk about at the end of the lecture. But in any case, um, the perspective, though, we need geometric cochains, which are something that Greg Friedman and Annabelle Medina and I have developed following Lipinski. And for that, you need a submanifold, or more generally, something that maps to a manifold. But I'm going to stick with submanifold, so this doesn't encompass the full definition, but this is an important special case for a geometric cochain. And if it's codimension D, um, and also co-oriented, in other words, the normal bundle in this case, it's just about the normal bundle being oriented, then you get an element, and I'm just still going to call it by the manifold's name, the submanifold's name, in geometric cochains, not cohomology, of M. And of course, this has to be a submanifold has to be proper. So think of, for example, the x-axis, the positive x-axis inside of R2 minus the origin. That's a geometric cochain. The relations of these to usual cochains, if you want, it's there's an intersection map. Well, maybe not a map, but some relationship that in some cases you could take this, like my W inside of R2, and to a smooth chain, which is transverse to it, I can I can associate this a function. Um, well, to a smooth chain, I associate a number, namely the intersection count of that chain with my W. So, um, so my W goes to something that we could call intersect with W and count, and that's in some sort of cochains. Well, it would be cochains transverse to W, smooth and transverse to W. So that's how a submanifold, you can think of it as a cochain giving a function by intersection. Um, but what we prove following ideas of Lipinski, so this is again with Friedman and Medina, and that's after Joyce and Lipinski. Joyce has his own version of this, but we took the Lipinski ideas and fleshed them out and extended them. So we've got submanifolds as cochain, so that's already geometric, hence the name. And now what we can do, and by the way, this is all sort of all conjectural, all things that I think should work, but we haven't taken the time to work out these details. Um, but what you can do is take W, and I claim there's a cochain that you could call bar W, and this will be in some sort of geometric cochain model for, or let me call it bar, for the geometric cochain model of in degree d minus 1 for the loop space, right? And I could just think of that as a formal object, but again, the idea is if regular geometric cochains evaluate by intersection, this one will evaluate by intersection after adjoint. So bar W evaluated, so this will sort of map to some sort of d minus 1 sufficiently transverse geometric cochains on omega m. And the way this evaluation would hypothetically go is that bar W evaluates on some um, d minus 1 simplex worth of loops by taking basically W intersect the adjoint of this, or in other words, taking the pre-image of under sigma adjoint, which goes from delta D minus 1 cross S1 to M of W. So let me write it this way. We're going to take just the pre-image of sigma adjoint of W. And again, sigma adjoint is going to go from delta D minus 1 cross S1 to M. And you check the dimensions, and since W is codimension D, um, the sigma adjoint pre-image is going to be codimension D in this D-dimensional space here, so I will get a count. And basically the idea is I've got a D minus 1 dimensional family of loops, and then I'm asking for one loop, maybe my W in this, I'm drawing it in dimension 3. My W is codimension 2 here. I've got a two-dimensional family of loops, and I say in the family, how many times am I intersecting W? So I'm counting things like this. The family of loops sweeps through and intersects W. So that's all well and good. That's kind of like a suspension or looping down of the cochain, however you want to, whichever language you want to use. But then we can define something like bar W bar V, and this is going to be the count of the, well, this is going to be roughly the number of times a loop in the family passes through W. So this is going to be the number of times a single loop, it's got to be a loop. You can't sort of hop between loops in the family. A loop in the family passes through W, then V. Okay. And right. And so that's all well and good. That's something that you can set up to, if I've got, then you can imagine defining this slightly more formally through adjoints and things like that and products. There's a product evaluation map. So we use delta 2 cross loops M to M cross M, and there's a little bit of a pullback and evaluate kind of thing happening is one way to make this formally well defined. Plenty of transversality needed. But now let's think about what should the co-boundary of this be. Now, going back here, going back to geometric cochains, if you think about this intersection idea, you find that you want the co-boundary of W to exactly be the submanifold represented by the boundary of W. And there's a little bit of an argument here. I'll leave it as an exercise that shows you that this count um, satisfies that relationship. In other words, if there's the value of W on the boundary of a chain is going to be given by intersections with the co-boundary. Sorry, anyways, intersections with the boundary of W will give you the value of the cochain W evaluated on the boundary of some chain. There's a little bit of a one manifolds classification argument where you think about the different possible you look at that chain in degree d plus one, and you think about the preimage of W, you're going to get some one manifolds inside a delta d plus one, and you track those boundaries, and you get exactly the co-boundary of W on the inside, or the preimages of the boundary of W on the inside of the simplex, and then by definition, the co-boundary of W on the outside. So here you would also see something similar. You would naturally see the co-boundary of this is going to be represented by the boundary of W. And what can happen is if W has boundary, so this is thinking of boundary operators as sort of a, almost in a more Drum theoretic way, like if things, if you've got a homotopy, then the boundary is going to tell you about what's going on. What are the difference terms? So suppose W had boundary here, and I have a one-dimensional family, sort of, it can kind of come off the boundary. And so there's one way that that can happen, that this count can change, namely the family comes off the boundary of W, and you get this formula here. Well, something different can happen here, namely the co-boundary of this expression. You are going to have up to some signs, and this one is even maybe some signs depending on how you set it up, but hopefully you set it up so that it's just plus. And then we can run off the boundary of V, and that's all well and good. But there's something else that can happen in a family. So remember, what we're counting is going through W and then going through V. So I've got my family of loops, and it misses them. And then in the family, I go through W and then V, right? Well, now imagine the family moving. Okay, and so that W then V thing happens later in this, or closer to a time where, well, eventually, in the extreme case, one loop in the family is going to hit an intersection point between V and W. So I'll put that intersection point there. So what happens is that this becomes plus or minus W intersect V. Now, intersection is product in the geometric cochains. It is product. It's a partially defined structure, but it is product. So this is saying that, and that's exactly the rule for what you get when you write down sort of formally in bar notation the geometric cochains. Sorry, the bar notation, the chains on BG, they form a bar complex structure where the differential is exactly this, using the multiplication. Now, we didn't talk about that so much in these lectures because G or chains on G, well, we could have developed this language more for our iterated bar discussion. So the way to bring it back to what we have been doing, though, the way I picture this is instead of bar W, bar V, I would just have a point going through W and then a point going through V, and in that order. And you see that, well, we talked about the fact that points could go off to the end, but if I meant base loops and W's disjoint from the base point, then that can't even happen. So I don't have to worry about those terms. I have quote unquote new terms because W and V are not assumed to be closed submanifolds necessarily, so they have boundaries. So the boundary of this can involve taking either the boundary of that or the boundary of that, or, they can come together. Okay. So there's a boundary term that way. So my three terms are these three. And you can see how this generalizes if I've got W1 bar W2 bar WK. I've got a sum of things where I can, again, if I'm thinking about this geometrically, I've got the boundary of WI that I'm running off of is a possibility. And, well, put the plus minuses there. And I can think about as I'm running from WI to WI plus one in a one-dimensional family, my intersections can, or my loops can be now not going through WI and then WI plus one, but just and in times in that order, but going through their intersection at one given time. I would still have WI minus one here. Okay. And so yeah, it's pretty much the same framework. It is the bar construction. So, the theorem, and again, I'll call it sort of conjecture because we're using geometric cochains, but it's a well-known theorem. So this is after, well, it's really sort of Adams, Hilton, and Eilenberg-Moore. That the bar construction on these geometric cochains of M, that gives you a model for the cochains of the loop space. Um, right. And it gives you more because that's just additively, but you can do product, and that's going to, again, should be intersection. And the intersection of conditions, because these are all conditions. My loop passes through W1, passes through W2. So one of De Morgan's laws says that the intersection of conditions is just satisfying their union, right? Um, and so that means that if I have like V1, V2, and W1, or just say W1, I'm going to, right, you end up shuffling the conditions. Um, so So this explains, you can present this as, hey, here's something you can do to this bar construction. You can shuffle things and you get a well-defined bar thing. And look, it's compatible with the boundary. But if once you believe this sort of geometric approach to the bar construction for cochains on a loop space, then thinking about what cup product should be, well, cup product is dual to intersection, or really is intersection if you're using geometric cochains. And the intersection of these sort of submanifolds of the loop space, these are submanifolds. If we can think about the condition of going through W at some point as a D minus one dimensional all loops which go through W sometime are a D minus one codimension submanifold of the loop space is another way to think about this. And then intersecting those means taking the union of their defining conditions, and that ends up being a shuffle product. Um, but of course, the loop space is, a monoid on the nose if you use more loops. And so that implies there's a homology product or a cohomology coproduct. And if you think about it a little bit, the product would of loops is concatenation. So you want to say that the coproduct is somehow concatenation, but of course it's dual to concatenation. So you're detecting concatenations, and yeah, I'll what that is breaking up bars. So W1 bar, W2 bar, WK goes to the sum of W1 bar up through WI tensor WI plus 1 bar WK. So you've got these um, product and co-product structures that the geometry sort of forces you to think about almost. It just leads you to these the shuffle product and again it's not just cohomology. Let me erase that. It's a cochain coproduct. Great. And then and so a good question that is something that I'm and actually some collaborators and I is to think about this for the free loop space. There you still have your parameterization. So you can talk about um, going through some manifold first and some manifold second because free loops are parameterized. But and you no longer though have the base point condition. So you can imagine these W's coming through the base point and going around the other side or vice versa. So that feels like various cyclic bar constructions. But again, I'm not going to work through that because I'm thinking about that these days a little bit. How does this really work with geometric cochains? But then let me also follow up on what we're saying that, well, if you notice, um, well, the product intersection is commutative. So we can do an iterated bar game. Again, intersection product is partially defined, and that's one reason I'm trying to be careful and use the word conjectural here, because even what you mean by bar construction on geometric cochains is a question that some collaborators and I are thinking about these days. Um, but in the iterated case, well, it shouldn't be that surprising that if I have a loops in M, I can be talking about when various points go to some W1, W2, W3, W4, and W5. And I can make some kind of cochain which says that there are 5 points in my domain, which is in this case n equals 2. So I'm looking at loops 2. 5 points in the domain. Um, the and maybe I should have called this W1 and this W2 to be consistent with the orderings I used in previous videos. I did my dictionary order as you should from based on X and then Y, but going to the right and then going up. Anyways, these are these iterated bar or Fox-Neuwirth cochains where I say there's 5 points in my domain. The first one goes to W1, the second goes to W2. Those lie on a line, on a vertical line. And similarly, on a vertical line, a point goes to W3, a point goes to W4, and a point goes to W5. And you can go through and make a complex out of these pictures and you get a model for the second loop space, um, third, fourth, fifth. So this is now saying that if you are looking at the question of can I compute the cohomology or even answer finer questions about loops in M, here's a model. Take the iterated bar construction on the cochains. And again, there's long literature of when this is good. Spoiler, this is good when n is less than the connectivity of m. You expect this to work really well. And when n is greater than the connectivity of m, there's plenty of things you can say, and it becomes a kind of an interesting question. Obviously, you're not going to answer everything about it because by adjointness, if you could easily determine the cohomology of this. The zeroth cohomology or zeroth homology is just going to tell you about the nth homotopy group of M. So you know you're going to run up eventually against some very hard questions, but the concept is pretty simple here. And let me even say, further conjecturally, um, that what you can do is for maps from X into M is you take sort of configurations in X and you decorate with submanifolds in M, and you look at subspaces of the mapping space like this and think of those as submanifolds. Now, if you're not doing an iterated bar construction, these won't give you cells. Um, Not unless you have a good way to maybe break down your manifold to somehow your domain to give you cells. Um, but by the way, the idea, furthermore, why you would even expect such models, I have said nothing about proofs here. The proofs, well, proofs often use something like a induction on ultimately things like the James theorem, which tells you about the a good small model for the loop space. But the philosophy of why you'd expect such things to work, at least in some favorable cases, is that if and I think this philosophy goes back to Poincaré, or at least I've heard people like McPherson talk about him initially saying, look, if I've got my manifold and I think about these places where I can kind of cut it and then, and they can be higher and higher codimension. And you imagine, and in some cases, like this W5 is the intersection of W1 and W2, or I could just call it W1 intersect W2. But imagine M being contractible when you take all of these away. So just imagine like a torus taking away the two homology or dually, if we're doing geometric cochains, cohomology generators, it's contractible. So there's no homotopical information that you see passing through those contractible pieces. And this is again part of the Adams-Hilton argument, part of the James theorem. You've got the basic idea is that mapping into, whether it's a loop or an iterated loop or a general map into something contractible is still contractible. So then the philosophy is that, oh, what I really need to do to understand a loop is understand how I hit these subspaces, because in between, nothing happens homotopically. Okay, so that's my philosophy for why these kinds of models exist. Um, yeah, so it's just something to you often see this subject. I mean, there's a lot of look, there's a lot of elegant ways to think about this. Let me tell you one more. For example, you could take the path space on your M and and think about the loop space as a pullback, and you get then the uh, you know you get this diagram where you think of the cochains on loop space have something to do with this diagram here. and you go from Tor on the cochains on M is a model for the and by Tor I mean the bar complex is a model for the cochains on loops M. So this is the ground field, and this is a ground field, and I can think about the cochains on M. So I've got a bimodule structure here, and that's fine. But for some applications and some extensions of these ideas, I like to think about submanifolds, think about these bar expressions or iterated bar expressions like this one here as um, prescribing these submanifolds that points in the domain with certain structure can map to. Um, yeah, and I'm hoping to make use of that in geometric topology these days. So connecting these standard mapping space ideas in algebraic topology with some things like Milnor invariance in geometric topology. Okay, I'm going to stop sharing and end the meeting.